சார் உள்ள விட்டுடலாமா சார்? 10 பேர் இருக்காங்க வெயிட்டிங் ரூம்ல.
சார் அட்மிட் பண்ணிடுங்க. ஏன்னா உள்ள வந்தாதான் இது பண்ண முடியும்.
பண்ணிடுங்கப்பா, பண்ணிடுங்க.
Welcome, sir.
Good afternoon, Karthik sir.
வணக்கம் கார்த்தி.
வணக்கம் சார். வணக்கம் சார்.
வணக்கம்
சார் கண்ணி உற்சவம் 2 உங்களுக்கு போஸ்ட் பண்ணுங்க.
கோகுல் குட் ஆஃப்டர்நூன். கேக்குதா?
ஒத்துமையா இருக்கணும்
சார். சார் வணக்கம் சார்.
மை பிரார்த்தனை கண்டினியூ பண்ணுங்க.
வணக்கம்.
சார் எப்படி சார் இருக்கீங்க?
நல்லா இருக்கேன்.
பார்த்து ரொம்ப நாள் ஆச்சு சார்.
अश्वगंधा का जूस पत्ती
ஹலோ ஹலோ
சார் குட்
ராம்குமார்.
சார் வணக்கம் சார்.
Yes sir, good
கோகுல்
evening sir.
வணக்கம்
Yes
வணக்கம்ப்பா.
sir. Good evening sir.
சார்
சரி. என் முகம் தெரியுதா?
சார்
கிளியரா
நல்லாவே
இருக்கு சார்.
சரி.
கிளியரா இருக்கு சார்.
ஐயோ, தேங்க்யூ. சரி வந்துட்டேன். என்ன கோகுல் என்னாச்சு
சார்
என்னாச்சு ஸ்டார்ட் பண்ணலாமா? மணி 3 போகுது.
ஆமா அதான் ஸ்டார்ட் பண்ணலாம் சார்.
3-1 இன்னும் 1 minute சார். எஸ் சார்.
ஓகே 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 ஓகே.
ஜாயின் பண்ணிட்டு இருக்காங்க சார். 86 ஆட் வந்திருக்கு சார். எஸ் சார்.
ஓகேமா ஓகேமா. சார் வந்துட்டாங்களா?
வந்துட்டார் சார். சார் வந்துட்டார் சார்.
சார் குட் ஆஃப்டர்நூன். அன்பழகன் சார்.
Sir, good afternoon. Good afternoon.
அதான் சார், எனக்கு இங்க என் ஸ்கிரீன்ல தெரிய மாட்டேங்குது சார்.
சார் ஸ்டார்ட் பண்ணிடலாமா சார்?
Yes, sir, we can start, sir.
எஸ் சார். மேம் நீங்க ஸ்டார்ட் பண்ணலாம் மேம்.
Yes, sir. The attitude should be positive like a proton. Doesn't matter how many electrons are around you. Good afternoon. With the blessings from the Almighty, we, the Department of Physics from Kondavaru Kandasamy Naidu College for Men, Chennai, feel privileged to welcome one and all present here. We thank each and every one for finding time and visiting today's webinar. I introduce myself as Dr. B. Pramina, Assistant Professor of Physics. Now, I would call upon Dr. G.R. Ramkumar, Assistant Professor of Physics, to give the welcome address. Over to you, sir.
Thank you, ma'am. A person who never made a mistake, never tried anything new. Albert Einstein. Good afternoon to one and all gathered here. It is my pleasure to welcome everyone to this wonderful occasion on behalf of the Department of Physics, C. Kandasamy Naidu College for Men. I would like to extend my warm welcome to our special guest of the day, Dr. G. Anbalagan, Professor, Department of Nuclear Physics, University of Madras, Chennai. I welcome Dr. P. Murugakuttan, Principal cum HOD of Physics, who has always extended his humble support for conducting this webinar. I welcome my staff members from the Department of Physics. Without their hard work and dedication, this event could not have been a reality today. I am also very delighted in welcoming the teaching staff members from various departments from our esteemed institution. I also welcome all the professors, associate professors, assistant professors, research scholars, postgraduate and undergraduate students from various parts of our country, as your presence had made this program a great success. Thank you.
Thank you, sir. That was a warm welcome. If we cannot do great things, do small things in a great way. This is what we have learned from our principal, sir. With no further delay, I would request Dr. P. Murugakuttan, Principal and Head of the Department of Physics, to deliver the presidential address.
Thank you.
Over to
Thank
you,
you,
sir.
madam. Thank you, madam. Respected invited speaker, Professor G. Anbalagan, the convener of this program, Dr. G.R. Ramkumar, and the organizing committee members, Dr. Gokul Raj, Dr. Karthik, Dr. Pramina, Rangaswamy, and Dr. Lakshmi Priya, and the participants from all over India and from abroad. I feel happy to take part in this webinar on perspectives of thermoelectric materials. And this is the program being organized by the Department of Physics of C. Kandasamy Naidu College, Chennai. And this is the department, one of the vibrant department of our college. The Kandasamy Naidu College was started in the year 1967, and this is running 54th year. And there are about 2,000 students are studying in this college in both shift 1 and shift 2. The shift 1 is for men and shift 2 is co-education department. Our department staff are not only involving in the academic work, they are involving themselves in the research activities also. As a part of the research activities, the Department of Physics is organizing this program for the benefit of the people all around India, especially in Tamil Nadu. The speaker that they have chosen for this program is Professor G. Anbalagan, Department of Nuclear Physics, University of Madras. I just to mention about him in a nutshell. He is an excellent teacher, a vivid researcher. Overall, he is a good human. I just wanted to register one thing here in this meeting. I'm thankful to him that he has nominated me as a fellow of Academy of Sciences after looking after my resume. Because of this Academy of Sciences, Professor Anbalagan is known to almost all the science faculties and all the science students all over Tamil Nadu. Sir, we are very fortunate enough in having you as our chief guest to deliver this lecture. And I take this opportunity to thank our management, the invited speaker and participants of this webinar. I hope these deliberations of this webinar are highly useful to the participants to enrich their knowledge in this potential field. I congratulate the webinar convener, Dr. Ram Kumar, and the committee members Gokul Raj, Karthik, Pramina, Rangaswamy, and Lakshmi Priya. Thank you. Wish you all good luck. Follow the SOP, Standard Operating Procedure of the Government of Tamil Nadu, and be safe. Thank you.
Thank you, sir. Now, it's time to introduce our special guest of the day, Dr. Sir G. Anbalagan, Professor, Department of Nuclear Physics, University of Madras, Chennai. To our esteemed audience, for which I would call upon Dr. S. Gokul Raj, Assistant Professor, Department of Physics, to go ahead. Over to you, sir.
அனைவருக்கும் வணக்கம். Good afternoon. At this moment, it is a privilege to invite and introduce Professor G. Anbalagan. I would like to say in Tamil, அவரோட மாணவனா அவரை அறிமுகப்படுத்துறதுல எனக்கு தான் முன்னுரிமை அப்படின்றத முதல்ல சொல்லிக்கிறேன். He has been known to me since my graduate days. A very enthusiastic teacher and very humble and honest gentleman. As our professor, Principal Murukuthan said, he is a very good academician as well as a researcher whose profile would justify his post as professor in University of Madras. He has also nominated me to Academy of Sciences, and that it is a privilege. I was also being nominated by the same Professor Dr. G. Anbalagan, who has been a stepping stone for many young researchers in the past, in the present, and also in the future. His publications in more than 100 Scopus indexed journals, which includes 84 research papers, 20 conference proceedings, crore of rupee funding from DST, MHRD, and RUSA, will explore his identity as a university researcher. He has been a board of study member in numerous institutions. For example, if you say a university, he will definitely have a nomination there. You say it, he will definitely have it. That is a simple word. He has been a member in academic, board of studies, and also in paper evaluation in Anna University, in University of Madras, in Trichy, Salem Periyar University, both as well as graduate and also as postgraduate. This shows his academic excellence. As a researcher, he has guided more than 10 researchers, and almost 8 researchers are doing research under his guidance. In MPhil, he has guided more than 25 research students. Apart from that, he is now guiding few researchers under his guidance, and also he has been a mentor, friend, philosopher, guide for hundreds of students. Many of his students has won best paper, best oral presentation, best thesis presentations at national and international level. He has been a convener for many science academic programs, NET, and also as a university exam coordinator. So I would like to introduce and like to be proud that the Department of Physics is having Dr. G. Anbalagan as its guest invited speaker in this special invited session. Now I welcome Professor Dr. G. Anbalagan. Sir, vanakkam, sir.
Good afternoon. My beloved friend Dr. Murugan and my beloved students, almost all the faculties of the Department of Physics in college is one or other way. They are belonging to my so all the students have arranged a function. I can say that they want to honor me because I am going to retire next to 2023. So they want to honor me. They are arranging this webinar. I can take in this way. So good afternoon to one and all. And once again to inviting me for a guest to give a lecture in the Department of Physics, Secretariat College, Chennai.
Thank you, sir, for your valuable presence. We are very glad that you are our guest for today's webinar. Now, without further ado, we will turn the time over to the guest of the day, Dr. G. Anbalagan. Sir is going to present a talk on the topic, Prospectives of Thermoelectric Materials, as Sir will provide us valuable knowledge on this topic. But before that, before Sir proceeds, it's a humble request to the audience to keep in good quality of sound functional during the meeting. Kindly mute yourself. And if you have any questions, please type them in the chat box and I will take up the questions at the end of the session. Wishing everyone a smooth transition for the next part of the event. Over to you, sir.
Thank you. So now also I can proudly say I am the alumni of the Pachipas College. One of the college belongs to the Pachipas. So this is, I think it is the time to start my lecture. Okay. Good afternoon. Today, I am going to give a lecture on prospectives of thermoelectric materials. Yes. So this is the power sector plant available in our India, and the data is on the August, based on August of 2021 data. See here, the most of our energy sources are fossil fuels, namely coal, lignite, gas, diesel. And this total fossil fuel covers about 60% of the energy we are using nowadays. And in the category of non-fossil fuels, which includes hydroelectric power, wind, solar, and other renewable energy sources, which comes around 39.6%, which includes the nuclear energy of about 1.8%. So the major parts of the energy comes from the fossil fuels. And also the table gives the data of the fossil fuels which are available in India now. So for the continuous usage of these fossil fuels, there is a depletion in the fossil fuels. However, the energy we have used goes on increasing. So in order to overcome this one, there is a lot of research is going on for the renewable energy sources. Unfortunately, the generation of thermal power station is inefficient process, and large amounts of energy are inevitably wasted in the form of heat energy. That is in the power station, thermoelectric power station. Large amounts of energy are inevitably wasted in the form of heat. Suppose if we take the modern coal-fired and nuclear power stations, there are about 37 to 38% these power stations are efficient. It means about 62% of energy released by burning coal or nuclear reaction is wasted. So more efficient gas-fired power stations have been developed, which are efficient of about 50% only. Hence, if electricity is generated at a power station that uses natural gas as the fuel, only 50% of the energy released by burning the gas is transformed into energy. So, in order to use this waste heat during the power production, sorry, 1 minute. I am unable to change the slide. So wait a minute, I will resolve it. Yes. So this, okay, please. So this diagram shows the various kinds of power stations and power production units that are available in our country. So this diagram shows only 34% of the energy produced is used. Remaining 60% is lost by means of the waste heat. So this waste heat can be converted into useful electrical energy by means of a technique called thermoelectric generator, and the materials that are used for generating electricity from the waste heat is called thermoelectric materials. You know, now India faces the energy crisis, and there is a depletion of fossil fuels for the continuous usage. And because of using fossil fuels, there is increase in pollution, and there is a wastage of energy in the form of heat. However, we need uninterruptible energy supply. So we need to go for renewable energy. So we are concentrate more on increasing interest in the renewable energy sources. That will increase the greenhouse effects also, greenhouse gases also. So to cover all these criteria, we are in a need of new technology to meet the energy demand and reduce the pollution. So the solution is certainly the thermoelectric material or thermoelectric generator. So the basics or fundamentals of thermoelectric effects. We have studied in our UG classes Seebeck effect. So Seebeck effect, immediately we should know what is thermocouple and thermopile. Thermocouple is nothing but two different metal wires connected at its ends to form two different junctions. Such an arrangement is called thermocouple. So when the junctions of the thermocouples are maintained at different temperatures, there will be thermo EMF developed in the circuit. The thermo EMF developed is directly proportional to the temperature difference between the two junctions. Such an effect is called Seebeck effect. So in Seebeck effect, the temperature difference between the two dissimilar electrical conductors reduces the potential difference across the junctions of the two different metals. So the cause of this potential difference is the diffusion of free electrons from high electron density site to a low electron density region. You know, the free electron density of electrons is different in different metals, and also it changes with the time. So here delta V is the EMF developed, and delta T is the difference in temperature between the junctions, and S is the constant of proportionality that is called the Seebeck coefficient. So normally in our earlier days, we have used two different metallic conductors to form a thermocouple. Now in the thermoelectric materials, we are using two different semiconductors. One is P-type and another one is N-type, like copper and aluminum in a thermocouple. Here P-type and N-type are two metal semiconductors that are used as the electrical conductors and compared with our metallic conductors in olden days. So a thermoelectric circuit composed of materials of two different coefficients, two different Seebeck coefficients, that is either P-type or N-type semiconductors, that constitute that is called thermoelectric generator. So the another effect is called Peltier effect. The Peltier effect is the inverse of the Seebeck effect. Here, an electric current is allowed to pass through a thermocouple. At one junction, heat will be evolved and another junction, heat will be absorbed. That is, one junction will act as heating junction and another one will be at a cooling. This is called a Peltier effect. So here we are using bismuth and the copper as the two metallic wires. We are connecting a battery for supplying current to this thermocouple. So this junction will act as a pole junction and the another one will act as the hot junction. So the Peltier coefficient is pi, which is defined as the coefficient of thermal current Q to the electric current I, that is Q equal to pi into I, where pi is the Peltier coefficient. So these are the fundamentals of the basics of thermoelectric thermoelectric generator or thermoelectric materials. So some of the important parameters that are related with the thermoelectric generators are: one is thermoelectric figure of merit. Thermoelectric figure of merit. The thermoelectric figure of merit, nothing but the thermoelectric performance, either power generation or cooling. Suppose we are using Seebeck effect for power generation. If we are using Peltier effect, we will get a cooling effect. So thermoelectric performance and the efficiency of thermoelectric material for transforming the waste heat into electricity. So the efficiency of the thermoelectric material primarily depends on the figure of merit of a thermoelectric material, and the figure of merit of a thermoelectric material is represented by ZT. So ZT is a dimensionless quantity or dimensionless figure of merit or quantity, which describes the efficiency of a thermoelectric generator. That is ZT equal to S square T sigma by K, where S square or S is the Seebeck coefficient, T is the temperature, and sigma is the electrical conductivity, and K is the thermal conductivity. That means the K is the total thermal conductivity. The total thermal conductivity is the sum of the thermal conductivity due to electron or electronic motion, and another one is due to lattice vibration. So Ke equal to Ke plus Kl. Ke, the electronic part, and Kl is the lattice part. The sum of these two will give the total thermal conductivity, that thermal conductivity here. So this is our conventional thermoelectric generator model diagram of schematic diagram of thermoelectric generator. So here the N-type and the P-type will covers one thermocouple, another N-type and the P-type constitute one thermocouple. So here there are 4 thermocouples connected. So such an arrangement is called thermopile. So thermopile, if more than two thermocouples are connected in series, that are called thermocouples, thermopiles. Here the thermopile is made up of the semiconductors. So the figure of merit is ZT, I already mentioned, S square sigma T by Ke plus Km. And Ke, the electronic part of thermal conductivity, Kl, the lattice contribution to the thermal conductivity. According to our Weidmann-Franz law, the Ke by sigma equal to L into T, or Ke, that is the thermal conductivity due to electronic contribution. Ke depends on sigma, that is Ke equal to L into sigma into T, where L is the Lorentz number and sigma is the electrical conductivity and T is the temperature at which we are measuring the thermal as well as electrical conductivity. So in most of the semiconductors, the Ke, the thermal conductivity due to electron, is less when compared with the Kl. It's less when compared with the Kl. So we have to control the thermal conductivity Kl so that we can increase the figure of merit. Because the ZT figure of merit is directly proportional to the Seebeck coefficient, electrical conductivity, and inversely proportional to the thermal conductivity. So we should decrease the thermal conductivity because we have to reduce the thermal conductivity by using some mechanism so that the figure of merit will increase. By at the same time, we should not, our mechanism should not decrease either the Seebeck coefficient or with electrical conductivity. So the power factor should be more, will be in, and lattice part of the thermal conductivity should decrease. That is the condition for our strategy to increase the figure of merit. The power factor, as I already mentioned, power factor equal to sigma into S square. For sigma, I have already mentioned Seebeck coefficient. Under a given temperature difference, the ability of the material to produce or convert electrical power is quantified by a term that is called power factor. So power factor equal to sigma into S square. Then the efficiency of the generator, like our Carnot engine, the efficiency equal to energy provided to the load divided by heat energy absorbed at the hot junction. That is Q by W by Q, like that. So the efficiency eta equal to TH minus TC. If you are substituting the energy provided to the load and the heat energy absorbed by the hot junction, you will get the efficiency equal to TH minus TC by TH, where TH is the temperature of the hot junction and TC is the temperature of the cold junction. So making use of this formula, we can able to convert the figure of merit into efficiency of the thermoelectric generator. So for a material of Z equal to 1, when the hot junction temperature is above 1200 Kelvin, the efficiency of conversion of waste heat into electrical energy is 19%, which is higher than the polysilicon solar cell. So this is our how the efficiency eta varies with the hot junction temperature. So by making use of hot junction temperature and the efficiency, you can calculate the efficiency formula eta equal to TH minus TC by TH into something, that formula. So these are some of the common thermoelectric materials: antimony telluride, lead telluride, and then silicon germanium, that all comes under P-type semiconductor material, having ZT value of about 1.8. The lead telluride is the material having highest the figure of merit value. However, the lead is the toxic in nature, so it will pollute our environment. And for the N-type semiconductor material, bismuth telluride is about 1. The figure of merit ZT value is about 1. These are some of the common thermoelectric materials. So we go to reduce or reduce the resistivity or increase the thermal conductivity, and decrease the or low thermal conductivity is required for reducing the high figure of merit. So reducing thermal conductivity without sacrificing the electrical conductivity or the Seebeck coefficient takes a considerable effort. The another one is thermoelectric quality factor. This is also nearly all thermoelectric materials are heavily doped semiconductors. So they have so many free electrons, and because of that, they have many properties similar to metals. The charge carry concentration. The charge carry concentration depends on the intrinsic defects such as the atom vacancy, as well as the intrinsic eccentric dopants, that is the impurity we have added. So because of all properties in the figure of merit, the Seebeck coefficient, electrical resistivity, and thermal conductivity depend on the charge carrier concentration and in a conflicting manner. In conflicting manner means someone increases with and someone decreases with. So that's for a good thermoelectric materials is really a search for material with high figure of merit ZT, presuming to be optimally doped. That is, we go to increase the carrier concentration. If I am using dopant means we go to increase the impurities. So this high figure of merit is determined by the thermoelectric quality factor. The quality factor B is equal to 8 by KB. KB is our Boltzmann constant. Me is our electronic charge, and then Me is electron mass, and E is electronic charge, H Planck constant, and mu W is the weight mobility, and KL is the lattice thermal conductivity. This shows because all are constant except in mu B and KL. That means mu B is directly proportional to mu W by K. Mu W by K. So this weight mobility and lattice thermal conductivity can be measured with the help of the Seebeck coefficient and thermal conductivity. Therefore, the potential of a new material can be estimated from a single sum. Another one is the weight mobility and the power factor. The weight mobility, I already mentioned mu W, and the quality factor is directly approximately equal to mu W by KL. So the weight mobility is nothing but, if you say take the Hall mobility is a function of Hall resistance and electrical conductivity. Like that, the weight mobility is expressed in a function of two properties, measured properties. One is Seebeck coefficient and another one is electrical resistivity or electrical conductivity. In the free electron model, this weight mobility equal to mu into m star by m power 3 by 2. M star is the effective mass and mu is the mobility, the Hall mobility. We can see Hall mobility. And then the electronic contribution to thermal conductivity, as I already mentioned, the thermal conductivity, the total thermal conductivity is the sum of electronic part plus the lattice part, that is Ke plus Kl. One is the electronic free electron or hole, and the other one is due to the phonon atomic vibration. So the electronic thermal conductivity derived from the same function, that is conductivity, and also determines the Seebeck coefficient and electrical conductivity. That means, I've already mentioned from the Weidmann-Franz law, the conductivity due to electron, thermal conductivity due to electron, Ke is equal to L into dt. Right? The another one is mobility and charge carrier concentration. So these are the parameters which are governing the figure of merit value Zt. These are governing the figure of merit value Zt value. So we have to get idea how to increase the electrical conductivity, how to increase the Seebeck coefficient, how to decrease the thermal conductivity. The another important parameter which is important for thermoelectric generator is mobility and charge carrier concentration. You know, in our semi-classical tube model, the 1 by rho, that is conductivity, and rho is the resistivity. 1 by rho equal to sigma, which is equal to n into mu, where n is the carrier concentration, E is the electronic charge, and mu is the mobility. Then the mobility, Hall mobility, or mobility of the electron equal to E into tau divided by mi star. I is the electronic charge, and tau is the scattering time, and I is the inertial mass. And mu h is approximately equal to mu. That is, Hall mobility is approximately equal to the mobility mu. We already mentioned a weight mobility, mu w equal to mu into m star by me. M star reduced mass and me is the electron mass power 3 by 2. And the Hall mobility is approximately equal to mu. So how the carrier concentration and Seebeck coefficients are related. To ensure the Seebeck coefficient is large, there should be only a single type of carrier. That means either electron or hole. So the mixed n-type and p-type conduction will lead to both the charge carriers move to cold end and cancelling out, and there is no possibility for inducing Seebeck voltages. Right? So the Seebeck coefficient is given by this equation, where all are constant except the carrier concentration. So if you are varying the carrier concentration, that is where n is the carrier constant, m is the effective mass, and the conductivity sigma equal to n into E into mu. If n increases, the conductivity increases. If conductivity increases, then automatically the figure of merit will also increase. However, if you lower the carrier concentration, because in these equations, Seebeck coefficient is inversely proportional to carrier concentration n. If you decrease the carrier concentration, then Seebeck coefficient increases. However, if you decrease the carrier concentration, that will decrease the electrical conductivity also. So the effective mass is also one of the important parameters, because we know the last expression mu W equal to mu T m star by m whole power 3 by 2. So the m star is the effective mass of the charge carrier. Charge carrier, which provides another conflict, as large effective masses produce high thermal power but low electrical conductivity. So the m star refers to the density of states of effective mass, which increases with a flat and narrow bands with a high. That means the m star refers to the density of mass. If the density of states of the effective mass, if the density of states are flat or narrow with a high density of states at the Fermi surface, then the effective mass will be more. They will contribute our figure of merit also. So the normal ways of optimizing the thermoelectric materials are to increase the power factor square sigma by optimizing the carrier concentration. That is the important value. By optimizing the carrier concentration only, we can increase the S square sigma value and reduce the lattice thermal conductivity by introducing different mechanisms. One of the mechanisms is the introducing the scattering centers in the material. So if you increase the scattering centers, the phonons will go multiple scattering, and finally the energy carried by the phonon will be less, so the thermal conductivity will be less. So these are the ways by which one can enhance the figure of merit ZT value. By alloying the semiconductors, introducing phonon scattering centers, nanostructuring the material, doping in the semiconductors, and cascaded devices, continuous arrangement of the thermoelectric devices. Suppose how will you use the alloying method in the case of bulk material? The major approach to enhance the thermoelectric properties in bulk materials is by tuning or doping and to vary the lattice thermal conductivity without affecting the electrical conductivity. I've already mentioned a good thermoelectric material with high figure of merit ZT is typically heavily doped semiconductors with low thermal conductivity. So the simple and commonly available thermoelectric material is the bismuth telluride. With interesting features, its Seebeck coefficient depending on its composition. An undoped bismuth telluride corresponding to 60 atomic percent of Te is B type with a Seebeck coefficient of about 230 microvolt per Kelvin. As the concentration of the telluride increases, the Seebeck coefficient gradually falls to 0, then changes the bismuth telluride into the N-type semiconductor. So the N-type semiconductor or N-type, the maximum figure of merit of P-type and N-type bismuth telluride crystalline materials at room temperature is about 0.75 and 0.86 respectively. That is without adding alloy. If you increase the concentration by alloying, this does decrease the conductivity, electrical conductivity, but lowers only the thermal conductivity. So in that case, in the low temperature region or if you add solid solubility, that is bismuth telluride, antimony telluride, and with bismuth selenide, the addition of antimony telluride and bismuth selenide to bismuth telluride improves the Z value. That means adding with bismuth telluride to another group, which increases the ZT value, and they are also reducing the low thermal conductivity, thermal conductivity, without too much degradation of the electronic properties. That means without decreasing the electric conductivity, it will increase the figure of merit, which is due to the reduction in lattice thermal conductivity. Right, and some of the another ways to increase the ZT value is to increase the phonon scattering. So if there are multiple or larger number of scattering centers, the phonon will go multiple scattering. So because of this multiple scattering, the energy carried by the photon will decrease. So the thermal conductivity also reduces. Right? And this can be possible, or this can be feasible work by the method such as MOX fluctuating scattering, that is by mixing or mixed crystal of ternary and quaternary compounds, and also by increasing inducing the grain boundary scattering. So due to large grain size, there is a scattering at the interface. Again, it will reduce the thermal conductivity. So another one is by forming a complex crystal structure, and then by forming multi-phase composites. These are the ways by which we can reduce the thermal conductivity. So our aim is to reduce the lattice part of the thermal conductivity, and without disturbing or without degrading much the electrical conductivity and the Seebeck coefficient. So these are the possible ways by which the phonon scattering undergoes in metals, in the materials. The first one is boundary scattering, and second one is imperfection scattering, and the third one impurity scattering, and this one corresponds to the phonon electron scattering. So by these four different ways, there is a possibility to produce reduction in the lattice thermal conductivity. So these are some of the schematic diagram for the grain boundary scattering, defect scattering, and then alloy scattering, etc. So we go to, and most of the semiconductors, the electronic part of thermal conductivity is less than the lattice thermal conductivity. So we have to decrease, or we have to control the lattice part of the thermal conductivity. So this is our optimization process. So these are the expressions we've already seen. So this is the maximum value corresponding to the ZT value, because S value is higher. So if the figure of merit consisting of S square, so ZT value will be here, and this here the corresponding the thermal conductivity is less when compared with, or the corresponding to this one. So what is the charge carriers? The corresponding charge carrier, that is 10 power 19 centimeter power minus 3. So we go to alloy, or we go to increase the concentration approximately 10 power 19 centimeter power minus 3. so that we can get the figure of merit value to the optimum value. So in the case of, the semiconductors, there are non-degenerate and degenerate semiconductors. In the case of non-degenerate semiconductors, in the case that is the thermal conductivity of electronic part is less than that of the lattice part, but in the case of degenerate one, this is greater than 1. So we are interested more in this one. So these are some of the commercially available thermoelectric generators. These are the materials having the very good value of ZT, that is around 1.5 to approximately 2, the materials. See, you can see from this diagram, the lead telluride and bismuth telluride is a novel material for this one. However, this lead telluride is more toxic in nature. So based on these fundamentals of this thermoelectric material, we will try to synthesize a nanomaterial with a good figure of merit, that is a copper telluride, by employing a ball milling methods. And the various characterization for measuring the electrical properties, namely Seebeck coefficient, thermal conductivity, and the electrical conductivity are carried out. So the material is prepared by ball milling method, and after ball milling method, it is dried at 100 degrees Celsius, and we use a hydraulic pressure at about 200 bar, and sintered at various temperature from 473 Kelvin to 973 Kelvin, and we can name these sample as CT1, CT2, CT2, CT3, CT4, etc. We are made into pelletized. So this pellet is used for measuring the Seebeck coefficient and then the electrical conductivity, etc. First, we have to confirm the phase of the material form. For that, we have used powder XRD, powder X-ray analysis. So the sample sintered between 473 and 873 of mixed phases, Cu 2.8 Te2 and Cu7 Te. So up to 873 Kelvin degree Celsius, we are getting mixed phase. And the obtained results are matched with the PDF files. When the sintered temperature increases from 873 to 973, we are getting a pure phase. With the space group P3M1, and no other secondary phases were obtained. So up to 873, we are getting mixed phase, and at 973, we are getting a pure phase. So this is our SEM image. The SEM image, we can see the size of the SEM image is approximately 80 to 90 nanometer, and mono dispersed. And also there is a well interconnected particles, also spherical image. So this is our EDAX analysis to measure the percentage of the, or confirm the formation of the material. So this is our coloring image. It acts with so here there is a homogeneously distributed in all the centered samples. There is no trace of oxygen or other impurities to obtain. And the distribution of tellurium is decreased with the increase of centering temperatures. So the TEM image, the formation of well-resolved lattice fringes confirms the high crystalline nature of the prepared sample. So in order to find the thermal stability, we've also recorded the combined TGDT diagram. There is a weight loss of 2% observed after 400 degrees Celsius, which is due to the removal of excess of telluride. And the sample from the TG analysis, we can infer the sample is stable around 400 degrees Celsius, stable around 400 degrees Celsius. So this is our XPS analysis to verify the oxidation state of the synthesizer material. We are getting two peaks, one at 950 degree, 950.62 electron volt, and 933.31 electron volt of the 773 sintered sample. The first one attributed to Cu2p 1/2, another one Cu2p/2 with a splitting of 19.31. And also for the sample sintered at 973 Kelvin, the peaks were observed at 932.8 and 952.6 with a spin orbit splitting of 19.82 electron volt. So when compared with the 8773 and 973, the spin orbit splitting is considerably increased, which confirms the phase transformation from tellurium rich, that is Cu plus to Cu to T, that is pure copper telluride. And also the presence of telluride is also verified by using XPS analysis by observing the doublet peaks at 572.8 electron volt or 583.4 electron volt, which indicates the TE 5/2 and TE 3/2 with a splitting of 10.33 electron volt. And then we have measured the electrical resistivity by making use of the combined experimental setup we are having in our lab. That is, that the instrument can measure simultaneously the conductivity, Seebeck coefficient, and thermal conductivity. So, making use of this instrument, we have measured the resistivity. The resistivity varies with the temperature as given in the figure. So, see here the CT6, that is the temperature, the sample sintered at 973 Kelvin will have maximum resistivity. Shows maximum resistivity, that is of the order of 1.5 into 10 power minus 15 at 330 Kelvin. And also the sample Ce2, that is the mixed phase, the low energy gap of 1.1 electron volt compared with our pure Ce2T. So this graph, from this graph we can be able to find out the resistivity. And then Seebeck coefficient. So the Seebeck coefficient, we are getting Seebeck coefficient. If the Seebeck coefficient values are positive, then the material is said to be p-type semiconductor. So we are getting the positive value of Seebeck coefficient. So it confirms the p-type semiconductor. And see here the Seebeck coefficient increases with the increasing temperature. So when the sample sintered to 573 Kelvin, that is CT2, the Seebeck coefficient is 5 million volt per Kelvin at 300 Kelvin. And it is increased to 55 million millivolt per Kelvin at 550 Kelvin. So the Seebeck coefficient increases with the increasing sintering temperature. That is the important result we have got here. So measuring the Seebeck coefficients, that means the sample sintered at below 773 shows a low Seebeck coefficient due to the mixed phases of copper telluride. So I already mentioned up to 773, 873 Kelvin, there is a mixed phase, and 973 Kelvin only we are getting the pure phase. So up to 773 Kelvin or 873 Kelvin we are getting the mixed phase. So because of the mixed phase, we are getting the less Seebeck coefficient value. So by making use of this power factor square sigma, we are calculating the power factor value. So this shows the variation of power factor with the temperature. And this is our measured thermal conductivity. And from the power factor and thermal conductivity, we have calculated ZT value. The ZT value. The ZT value increases again, also increases with the temperature. So here, the sample that is CT6 sintered at maximum or 973 Kelvin, or the sample at pure phase shows the maximum ZT value. Maximum ZT value, the two of the order of 0.035. So we obtain the figure of merit of the order of 0.0325. It is a less value, but it is a higher value when compared with the report literature, because ZT value mainly determine the efficiency of the thermoelectric generator, but the efficiency value we are getting only 0.03 ZT value, figure of merit value. So we can increase the figure of merit value by using XPS method, that is spark plasma centering. That is, before making measurements, the Seebeck coefficient or thermal conductivity and electric conductivity measurements. If you are using if you are pressing or if you are using XPS technique, then there is a possibility to increase the figure of merit value by 10 times. It was already proved that the SPS method is one of the methods to increase the figure of merit value, because it increases the Seebeck coefficient value, so that the figure of merit value will also increase. So these are the results. So we already mentioned, we get power factor value of 102 at 550 Kelvin, but the ZT value is 0.035. But not to increase the ZT value, we are trying to use the facility SPS method. If we use this SPS method, there is a possibility to increase the ZT value or figure of merit value. Right. So once we know the ZT value, we can able to calculate the figure of merit. We can able to calculate the efficiency. From the efficiency, we can able to, if the efficiency is considerable, then we can able to make a thermoelectric generator. These are the one material I have. On this material we will synthesize, and the instrument is about from the project obtained from the DSTs. So like that we go synthesize the different material, copper, nickel, tin sulfide, and this shows why we are this material has a different or interesting morphology, that is flower-like morphology. So what is the specialty in the flower-like morphology? The easier petal in the flowers will act as the scattering centers. So there is a possibility for increasing the scattering centers. So there is a, if we increase the scattering centers, there will be more number of photon scattering will take place. So the thermal conductivity will be less. This is the one of the material we have synthesized, and we have obtained this flower-like structure. So this is our original flower. We are compared with our flower-like morphology. So almost we are getting the flower morphology for this material. And these are the results corresponding to this material. And here also we are getting the power of or ZT value will be of the order of 0.25, but it can be increased if we are using again the XPS method. So we are trying to use the XPS method, and also by alloying we can use we can increase the ZT value, so that we can increase the efficiency of this. So these are some of the materials we already published and having the figure of merit value. One is 0.22 at 708 Kelvin, and another one 9.5 into 10 power minus 4 is oxide material. Oxide materials, it is not possible to get more figure of merit value, and this is the already above present value. This one we have submitted. And both these works are supported by the funding agency. One is the DSS and another one is the Stars MHRD, the projects. We are having, we have measured, not, I think we have calculated the ZT value, but so far we didn't calculate the mobility. Mobility charge carrier concentration. That means we didn't study the influence of charge carrier or the concentration of charge carriers on the Seebeck coefficient, because we are not having the facility to measure the mobility. However, we have purchased or we have ordered the instrument for the Hall effect measurement system from the Stars MHRD project. We will get the instrument very soon. That is probably within a month. If we are getting the instrument, we can calculate the figure, the carrier concentration. From that carrier concentration, we can change the Seebeck coefficient value. Then it is possible to increase the figure of merit. Then in turn, we can increase the efficiency of the thermoelectric generator also. So these are the few works we have done in our lab by our research scholars that I will present. Thank you very much.
Thank you, sir.
Thank you, sir, for giving in your valuable insights on the topic. So that we will go ahead with question answer session, and we have a few questions posted in the chat box. Sir, can I go ahead with the question, sir?
Yeah, yes.
Thank you, sir. Sir, one of our participants, Vaishnavi ma'am, has shooted up the question, which is the best thermoelectric material which can be used, sir?
Yeah, that is lead telluride. Is so far proved that the receptive value will be high, but it is a toxic in nature. But it is toxic nature, it will affect the environment. That is the issue.
Thank you, sir. The next question is from our participant Gokul Raj sir. Can we have an oxide type of thermoelectric material?
What type of?
Can we have an oxide type of thermoelectric material?
Actor.
Oxide.
Oh yeah, oxide type of thermoelectric materials are available. They are doing a lot of research is going on the oxide thermoelectric materials. But only drawback is the figure of merit value is not that much expect.
Thank you, sir. So the next question is from Gaurav Jamwal sir, who's asked, why is the Z multiplied by the temperature?
Because it depends on temperature. To show the dependence of the figure of merit value with the temperature we are.
Okay, sir. Thank you, sir. The next question is from Krishnaveni ma'am. Which material has got high temperature and which has got low to produce a good quality of temperature sensor?
Yeah, temperature sensor, that is different.
Okay, sir. The last question, sir. It is posted from Ram Kumar sir. Is there any difference between intrinsic carrier concentration and equilibrium concentration?
Yeah, intrinsic concentration that mainly depends upon the pure form. If you take silicon semiconductor, silicon or germanium, that is pure. But in the case of extrinsic, we are adding the impurity. But in the intrinsic semiconductor, there is any defects. It's if the equilibrium concentration will differ.
Thank you, sir. Thank you very much, sir. I hope this answers your questions. With this, we wrap up the question answer session. Thank you very much, sir, for being in so patient and answering to all the questions. The feedback form has been posted in the chat box. Kindly fill in it and send it back to us. And we will be posting your certificates at the earliest. I think we are good enough for now. We will meet back soon. Now I call upon Dr. N. Karthik, Assistant Professor, Department of Physics, to deliver the vote of thanks. Over to you, sir.
Thank you. Good evening to one and all present here. It is such an honor for me to get the opportunity to thank all. On behalf of our Physics Department of C. Kandasamy Naidu College, I would like to express my gratitude to our Honorable Chief Guest Resource Person, Dr. G. Anbalagan, Professor, Department of Nuclear Physics, University of Madras, Chennai. Thank you, sir, for the inspiring and enlightening us with your words on this occasion. Your speech gave us a deep insight into the topic and revealed some interesting fact to us. Thank you, sir. A special thanks to our principal and HOD of Physics, Dr. P. Murugakuthan, for providing immense support to make this webinar successful. Thank you, sir. I would like to extend my thanks to our convener, Dr. G. Ramkumar, Assistant Professor of Physics, Department of Physics, to organize the webinar even in the pandemic situation. I must thank our organizing committee, Dr. S. Gokulraj, Assistant Professor of Physics, Dr. B. Pramina, Assistant Professor of Physics, Mr. C. Rangasamy, Assistant Professor of Physics, and Dr. V.S. Lakshmi Priya, Assistant Professor of Physics, for working hard for the first few days to make this webinar grand successful. Thanks to all. I would like to congratulate all the participants for their active participation. Thank you everyone once again for making this event a grand success. Thank you all. Thank you, ma'am.
Thank you, sir.
Sir, Anuragan, sir.
Yes, sir. Yes, sir. Thank you.
Sir,
Thank you very much.
Thank you, sir. மகிழ்ச்சி. எங்க பசங்க வந்து இன்டர்ன்ஷிப் ஏதாச்சும் கேட்டாங்கன்னா கொஞ்சம் கொடுங்க சார்.
Definitely. Work for me, sir.
Sure. Thank you very much.
Thank you, sir.
Congratulations all the organizing members.